Okay, so let's continue talking about the sup and the inf. That's what we began talking about last time. I hope you remember the sup of a set A is the least upper bound, and the inf of a set A is the greatest lower bound. Right, and we did a couple examples last time. How about, let's try, I don't remember exactly what we did last time. How about this set? Let's say A is, I'm going to write this as an interval. The interval from 0 to 5, and I have it open on the 0 side and closed on the 5 side. So this means all numbers greater than 0, not including 0, and less than or equal to 5. What are the sup and the inf of A? What do you think? Anyone want to tell me the sup of A? Yeah.
5.
5 is right. 5 is an upper bound because everything in the set is less than or equal to 5, and it's also the least upper bound, the smallest such number. So the sup of A is 5. How about the inf? It is 0. Yeah. 0 is a lower bound. Everything in the set is greater than 0, and 0 is also the smallest possible, the greatest possible lower bound, right? So 0 is the inf of A. Excellent. Any questions about sups and infs? This is the sup and the inf. How about, I got a fancier example here, and I also figured out, I think, how to turn the page. I think. Yeah, did you see that? I don't know if that's better than just sliding it to the side. How about this? I'll call it S this time. The set of all x such that x squared is less than 2. All right? I hope you're used to reading sets that are written in this way. This is the set of all numbers x such that x squared is less than 2. You may take a moment to think about what that set is. For instance, 0 is in this set because 0 squared is less than 2. But something like negative 100 is not in the set because negative 100 squared is greater than 2, right? So think about it. Maybe I'll let you guys think for a moment on your own. What do you think? I'll give you until the clock says 2:05. I want to know what is the sup and the inf of this set. You can talk to your friends and neighbors if you got any. All right, the clock says 2:05. What do you think? Anybody figure out? Think you figured out what is the sup? You can shout it out. I heard someone say the square root of 2. I agree. The sup is the square root of 2. This would be, the set is all numbers such that when you square them, the answer is less than 2. Actually, you could think about shouldn't draw right there. You could try to make yourself like a little diagram. This is the real numbers. Some of them, when I square it, it's something less than 2. Some of them, when I square it, it's something bigger than 2. I don't know if it helps to make a diagram, actually, now that I think about it. Maybe you can think of the graph Yeah, the diagram is not terribly helpful. So, like 0 is part of this set S, and if you get slightly bigger than 0, it's still true that the number squared is less than 2. Anyway, once you hit root 2, I think this set goes all the way up to, but not including that point, right? All the numbers less than that, when you square them, the answer is less than root 2. And then for negative numbers, so that means the sup of this set would be the least upper bound for those numbers, which would be just that point on the end. It is the square root of 2. What did you say for the inf? Of course, for these questions, sometimes it's possible there is no sup or there is no inf. If the set, for instance, is not bounded above, then there's no sup. What do you think about the inf?
Negative root 2?
Yeah, I think negative root 2 is the answer for the inf. For the same reason, if you think about it, this set goes in the negative direction. It goes all the way back to, but not including minus root 2. And so the sup and the inf are root 2 and minus root 2. In fact, actually, if you agree with my thinking here, the original set S, as a set, it is just equal to this, right? It is the open interval from minus root 2 to root 2. And the sup and the inf would just be the top endpoint and the bottom endpoint. All right? Any questions about that? Great. This one, that's a little slightly stranger example. Okay. I want to talk today, our sort of big topic for the day, which I said we were going to talk about last time, but we didn't quite get to it, is what we call the axiom of completeness, or the completeness property of the real numbers. This is really, from a theoretical point of view, this is what separates the real numbers from the rational numbers or other kinds of sets, is the completeness, right? We've already said the real numbers are an ordered field, but so are the rational numbers and other types of numbers. But what's different about the real numbers is that they are complete. I said last time that means that there are no gaps between them, but that's sort of an informal way of thinking about it. The technical way that we write this completeness property is called the axiom of completeness, and I'll just write it down. Here's what it is. It says if any set, I'll call it A, subset of the real numbers is non-empty and bounded, then sup of A exists and is a real number. All right, this is called the axiom of completeness. And it just says that every bounded non-empty set has a sup, and the sup, it exists, and it is a real number. It's actually a number, right? It's written like a theorem because it's telling you something that is true about the real numbers. But actually, this is called an axiom, and typically you would not try to prove this about the real numbers. This instead should be considered as part of the definition of what the real numbers are. The real numbers consist of numbers, and you include enough of them so that every possible bounded non-empty set, the sup of that set also counts as a real number. All right. So this is not typically proven. That's why it's called an axiom, because it is, axioms are things that you don't try to prove. They're just part of the definitions of these things. All right. I will point out, I'll just say note that Q, the rational numbers, does not satisfy this axiom. Does not satisfy, the book writes this, AOC, the axiom of completeness. The rational numbers does not satisfy this because it is possible to have a set of rationals where the sup of that set is not a rational number. And we saw an example like that. If I take the sup of this set, 3, 3.1, 3.14, etc., the sup of that is pi, but these are all rational, so these things are all in Q, but this thing is not in Q. And so for this reason we say the rationals do not satisfy the completeness axiom because it is possible to have a set of rationals which is bounded and not empty, but the sup of that set is outside of the rationals. So the rationals are said to be incomplete for that reason. They don't include all the sups. But the real numbers are complete because they do include all the soups. They also include all the inf, although it's not necessary to say that as part of the axiom. In fact, if you want to prove that the inf always exists and is a real number, you can prove that using this axiom, like as a theorem. You don't have to assume it. Okay, this is the axiom of completeness. I want to talk about, in a little bit more detail, about the soup. Technical things about the soup. So maybe I'll just call this sort of two theorems describing the soup. The first one will be very obvious, just a more technical way of writing what the soup is. It's the least upper bound, right? So let's just start off with the first one. It says this. So for some number S, in the real numbers, and some set A, a subset of R, then S is the soup of A if and only if two things are true. First of all, I'll write them down and then we'll talk about why. This is going to look like sort of a bunch of nonsensical symbols, but if you can decode them properly, it's actually very easy what I'm seeing here. So the first one says for all A in the set A, S is greater or equal to A. And the second one says for any upper bound B of the set A, S is less than or equal to B. All right. So the theorem says that some number is equal to the soup. What that means, if and only if, means it's completely equivalent to the other part, and the other part has two things. The first says that for all A in A, S is greater than or equal to A. In other words, you just say this means that S is bigger than everything in the set A. In other words, there's a more sort of colloquial way of saying that. What does that mean? In more plain language, S is bigger than every element of A. We have a word for that. S is no, well, just the first part by itself doesn't mean that S is the soup. It means I'm saying for every element of A, S is bigger than. I would say this means S is an upper bound. So you're going to say? All right. S is an upper bound, right? This is just a more like sort of symbology. Symbolic is the word I'm looking for. A more symbolic way of saying S is an upper bound. Just for every element of the set, S is bigger than that element, right? And the second part, for any upper bound, S is less than or equal to B. That means that S is less than all the upper bounds, which is to say S is the least of the upper bounds. So the second part means S is least, right? So all this theorem is saying really is in two very more specific technical ways. Saying the first part just says that S is an upper bound. The second part says that S is the least among all the upper bounds. So that's why this is equivalent to saying S is the soup, right? The soup means the least upper bound. All this theorem is doing is sort of splitting that out into two parts. There's no, we don't really need to prove this. It's obviously that these are the same. I'm just saying the same thing in a more symbolic way. All right, so that was the first of the two theorems describing the soup. The second one I do want to talk about in more detail. I'm going to slide that up. All right, theorem number 2. This one's more interesting, I think. Actually, before I write down the theorem, let me just say, I'll try and sort of give you a little intuitive feel for what we're going to say. So we can describe the soup in terms of some language like that. Some sort of really close points, all right? A lot of, like I've said before, a lot of what we talk about in this class is going to involve describing things in terms of numbers, this or that number being really close to some other number, right? We can describe the soup in this way also. For example, if I have a set of points that's like A, maybe A is a bunch of points like this, right? Where on the picture would you expect to find the soup? You would expect to find the soup like right on the right-hand side of those points. So if this set is A, then this is the soup of A. And I'm going to say, informally speaking, and this is what the theorem is going to say this like for real, but in informal language here, I would say something like the soup of A is the something like the point on the right side. The inf would be the one on the left, but the soup is the point on the right side, which is, could we say, really close to A, right? It's the point on the right side, which is like as close as you can get to the points of the set A, all right? That's the intuitive notion of what the soup represents. The inf, of course, would be the same, but on the other side. It's like the closest point you can get to the set A on the other side, all right? This is what I want to express in more formal language in the other theorem. And to get this idea of really close, just like last time, the closeness will be expressed by the phrase for all epsilon greater than 0, and then you say some stuff. I don't know if you remember from last time, but this is like the cute way that you can talk about points which are really close to each other. You actually say it in terms of all real numbers that are greater than 0. It turns out to only be interesting for the really small ones. Anyway, here's how we express this. So it starts off like this. So I'm going to say let S be an upper bound for some set A. And then S is the soup, right, with an equal sign. S equals the soup of A. If and only if. Here's my business with the epsilons, all right? It's going to look a little crazy. Let me just write it first and we'll try to explain it. For all epsilon greater than 0, there exists some number A in the set A such that S minus epsilon is less than A. All right? This bunch of nonsense over here is a formalized or symbolic way of expressing this idea about S is like the closest point that you can get on the right side of the set A. This is kind of like, I mean, what it says in the box there. That's like it's like Hollywood mathematics. When they have math in the movies, they want to make it look as complicated as possible. They do things like that with the. They love that for all and there exists because they look weird. Can I just try and decode what it says in the box there? Because it looks pretty crazy on the surface. What I would say is, think about this point S, right? Which is supposed to be the soup. It's this on the end, right? That right there is supposed to be S. What the thing in the box says is, if you move the S to the left a little bit, that's what the S minus epsilon means. You think of epsilon as being some very small little bitty number. What this says right here, if we move the S to the left a little bit, then that's S minus epsilon, then that resulting thing will actually be less than one of the elements in the set, all right? So on this picture, it means if you were to take this point and push it to the left ever so slightly, pointing to your right, I mean this way on the screen. If you push it to the left ever so slightly, you'll end up going less than one of the elements of the set A, all right? And this is what I meant, intuitively speaking, by saying S is like the closest you can get on the right side without overshooting any of the values. It says if we were to subtract any number from S, we will in fact overshoot one of the values from the original set. All right? It's a cute way of saying that. You know, a lot of real analysis is kind of learning how to speak in this weird language of for all epsilon greater than 0. There are so many things that you can express using that term that are hard to express any other way. Sometimes impossible to express any other way mathematically. All right, I want to see if we can do the proof of this. I don't want to go too crazy doing proofs all the day long, but this one is important. I don't know about you. I can do proofs all day long, but I know not everyone has the same lifestyle that I do. So let's do, this is a if and only if, right? So you got to do two separate things. Let's do this way around first. So we're going to assume S equals the sup of A, right? And what we need to show is all of that stuff on the right-hand side. Now, this is some very important structural ways that we're going to prove things, because it will come up very often in this class that you need to prove something which looks like this kind of a thing. It begins with a for all epsilon and a there exists right afterwards. Here's how we do it. We have to prove what's in the box, so I'm going to say it this way. Let epsilon greater than 0 be given. This is a phrase you will see a lot in this class. We have to prove something is true for all epsilon greater than 0, because that's inside the box, right? What we need to prove is something about all epsilon. So you begin by saying, okay, let's imagine that we had some epsilon which is greater than 0. The typical way of saying that is let epsilon greater than 0 be given. And then we will, we in fact need to demonstrate that there exists some element A which has this property. So I'm going to say we will find A in the set such that S minus epsilon less than A, right? This is what we have to do. So imagine that epsilon is any number greater than 0, and we have to find some element from the set that obeys that S minus epsilon less than A. All right? Okay. There's a lot of kind of notation to wade through here, but actually the proof is not so difficult if you based on one simple fact. So I will maybe say, note that S minus epsilon is less than S, right? It definitely is. S minus epsilon means S minus a little bit, and that certainly is less than S. And so, since S is the sup, sup, remember, is the smallest possible upper bound. This means S minus epsilon is not an upper bound of A. Right? Because S is the smallest upper bound. And so if you subtract a little bit, get something else, whatever it is, it cannot also be an upper bound, because it's less than S, which is the smallest upper bound. All right? S minus epsilon is not an upper bound of A. Anyone want to help finish this off then? What we have to do is find some, or demonstrate somehow that there is some A which obeys this. Any thoughts? Yeah.
Like, well, since the S minus epsilon is not an upper bound of the set A, there must be a value in set A that is bigger than
Yeah, right. Since S minus epsilon is not an upper bound, it means there is actually an element of A which is bigger than that. That's what it means to not be an upper bound, right? That means there are things that are bigger. So S minus epsilon is not an upper bound, so it is a fact there does exist some A in the set with A greater than S minus epsilon. And this is what we need to show, right? So I will say, I have an old analysis book actually, like from like 1912 or something, and at the end of every proof they write "shown" to mean like I have showed it or something like that. So sometimes I write that at the end of a proof. Shown, all right? There is a set, if S minus epsilon is not an upper bound, then that means there is some element which is bigger in the set. And that is what we had to demonstrate. All right, that's just this half of the proof. Remember, the proof has two parts. Let's talk about the other one. And then we'll get to something which is a little easier to talk about, not proofy. Do you remember what it said? It's up there. So this time we assume the stuff in the box, and we must show that S is the sup of A. All right, so this time around we're going to assume, there's no easier way to write this really. We assume for all epsilon greater than 0 there exists A in A such that S minus epsilon less than A. And then I want to show that S is the sup of A, right? Sorry, and we also assume this was at the very beginning of the theorem. The theorem at the very outset says let S be an upper bound. So we actually don't have to show that part of being the sup. Remember, the sup means it's an upper bound and also it's the least upper bound. We have already assumed that S is an upper bound. So can I maybe add this in here? Assume blah, 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 blah. Can I add it over here? Sorry. And assume S is an upper bound. All right. And then what we want to show is that S is the sup of A. All right. That is to say, we just need to show that S is the least upper bound. Okay. S is the least upper bound. This one is easiest, I think, to do by contradiction. So I'm going to say, let's assume in order to get a contradiction, for the sake of a contradiction, assume that S is not the least upper bound. That is to say, there exists an upper bound B, which is less than, strictly less than S. All right? If S is not the least upper bound, that means that there's another bound, upper bound, which is less than S. And so I'm going to assume that there is another upper bound, B, which is less than S. Yeah, that's what, sorry, my paper says something wrong. On a picture, what we're talking about is here's my set, A. Somehow S is here, but B is less. And they're both upper bounds, all right? I want to somehow get a contradiction with this stuff in the box here. We have to somehow contradict with these symbols. For all epsilon greater than 0, there exists A such that S minus epsilon is less than A. Check it out. Here's the proof ends fairly easily by just saying let epsilon equal S minus B. See, our assumption here will hold for every possible epsilon. So we can decide what we want the epsilon to be. You imagine epsilon is some really small number. And it makes sense, given the picture looks like this, to choose this little amount here as my epsilon. And then what I have to do is I want to show that S minus I want to show, sorry. Confusing myself. We have assumed the stuff in the box over here. We assume for all epsilon greater than 0, there exists A such that S minus epsilon is less than A. So what that means is, then there exists A such that S minus epsilon, but I'm using epsilon B, S minus B, is less than A. All right? This, of course, we can simplify. What do you get when you simplify the thing on the left? Yeah, just B, right? The S's cancel. The minus signs give you just a positive B. So B is less than A. And this is a contradiction with the assumption that B was an upper bound for this set, all right? Because I've just demonstrated that B is less than one of the elements in the set. So, or let me just say this. I'll say it this way. So B is not an upper bound. So this contradicts right here, right? Where we assumed that B was an upper bound. All right, and this is really the end of the proof. This one is a little taxing. Does anybody have any questions about that? This is meant to be sort of a warm-up to the kinds of things that we're going to be talking about throughout the semester. This one's a little tricky, but there will be a lot of little epsilons. That's something to look forward to, or maybe not, depending on how you feel about it so far. I'm looking forward to it. All right. What I want to talk about for our remaining time is a fun consequence of the completeness property. So this was the just sort of two theorems about the soup, and we're done talking about those two theorems about the soup. It's actually the next little section in the book is called, I think, Consequences of the Completeness Axiom. I think that's the name of the section. There are 2 or 3 major consequences. The first one I want to talk about is, so this is a consequence of the completeness property. And it is called, this is another important property of the real numbers, which is not true of other sets of numbers. It's called the nested intervals property. And this one is what we're going to talk about the rest of today's, is considerably less technical than what we just did. So if you totally zoned out, you can start paying attention again. The nested intervals property is about what happens if you have nested intervals. What I mean by that is if we just have a bunch of different intervals, and for now I'm going to say they're all closed intervals, and you have like a sequence of intervals. I1 is some interval, I2 is some other interval, I3 is some other interval. So in general, IN, I'm going to let IN be a different interval. Each of these has 2 endpoints, right? And I'm going to consider them to be all closed intervals. And we're going to take infinitely many of them. So there's a I1, a I2, a I3, etc., all the way up, all the way down, all right? And we're going to assume, so that's a bunch of intervals. We are also going to assume they are nested, and what I mean by that is assume that IN plus 1 is a subset of IN for each n. So that means I1, for instance, if you read this with n equals 1, it says I2 is a subset of I1. And similarly, I3 will be a subset of I2. So the biggest one of all is like I1. I'm going to try and sort of draw a little diagram here. I1 is some big interval like that. It's a closed interval, which is why I put those square brackets on the 2 ends. I drew a wiggly line there because my hand hit my leg as I was going across. It's supposed to be a straight line. This is an interval. And then the next interval, I2, is like something like this. It's a subset of I1, right? And then I3 is a subset of I2. Now they may actually match up at one of the endpoints. That's okay. And in fact, they could be entirely equal if you want. But anyway, this is what I mean by a sequence of nested intervals. Just each one is inside the previous ones, all right? This is called a sequence of nested intervals. The theorem, or the nested intervals property, is about what happens if you take the intersection of all of these. So I'll put a little ... These go on forever. You imagine you have an infinite bunch of nested intervals. And what happens if we take the intersection of all of these? So what can we say about the intersection? I'm going to write it this way. N equals 1 to infinity, the intersection of IN, all right? This intersection means I want to only consider those points which are inside all of those intervals. All right? For example, I hope you got the picture here. For example, if I have something like IN equals closed interval minus 1 over n to 3. What does that look like? Well, we can try and draw them. Maybe you don't even need to draw the picture. We can just plug in. The first one looks like minus 1 to 3, right? I plug in n equals 1. I get minus 1 to 3. The next one, I2, looks like minus 1/2 to 3. I3 looks like minus 1/3 to 3, right? So each of these, if you were to draw them on a number line, here's 0. The first one is like that, right? Where this is 3. The next one would be instead of starting, so this is minus 1 here. So this is I1. This would be I2, right? It goes from minus a half up to 3. The next one, I3, is going from minus a third, which is like there somewhere, up to 3. This is I3, etc., right? Then what is the intersection? N equals 1 to infinity, In. In this example, what do you think? What would the intersection be? I'm asking about what are the points, even if we continue this forever, these nested intervals, shrinking them down each time forever, is there anything left afterwards? Or do they just like shrink to nothing completely? What do you think? Yeah, the interval from 0 to 3 is going to be left over. And should it be, so it's going to be like this. Closed interval at 3, because 3 definitely isn't all of those intervals. What about the 0 side? Should be a square bracket or a round? Yeah? The curvy one? You got to ask yourself, is the number 0 actually in all of those intervals or not? Yeah, so I think 0 actually is in every one of those intervals. That means in the intersection does include 0, right? So the intersection of these nested intervals is the interval from 0 to 3, closed interval from 0 to 3, all right? So this is the setup, right? The theorem which we're about to talk about is something about what happens when you take an intersection of nested closed intervals. Here's the theorem. I'll write it down. It's actually not hard to prove, and I want you guys to see if you can do this. I'll give you some serious hints. But so I'm just going to say let In be a sequence of nested intervals, which means what I said before about they're all closed intervals. Nested closed intervals. All right, it means they're all closed intervals and each one is contained inside the previous one. All right. Then, here's the theorem. The intersection n equals 1 to infinity, In, is not the empty set. All right. In the picture that I just drew, all those intervals contained that big chunk on the right-hand side. But even if you shrink both sides at the same time, what the theorem says is the intersection of all the intervals can never be the empty set. There must always be at least some point in all of the intervals. All right, that's what it says. I don't know if you believe that, but let's see if we can demonstrate this. Like I said, we got 10 minutes. I think that's good enough. So let me just say informally to start off, we must find some number in every interval, right? That's what it means to say that the intersection is not empty. It means that at least one number exists in all of them, all right? In the example I drew, there were many numbers in all of them. That's not necessary to show that. And the first of my hints is we will use the axiom of completeness, because I said this is meant to be a consequence of the axiom of completeness. We will use AOC, the squad. I'm talking about the axiom of completeness, all right? Remember the notation that I used above. I'm going to write it this way again. My intervals, each interval is going to have the two endpoints. I call the left endpoint A-N every time and the right endpoint B-N every time. And here's the big hint. I'm going to let X be the sup of the set of all A-Ns. So, the set of all the left endpoints. It is a set. It has a sup. Does it have a sup? Are you sure that that set is bounded? I think it is bounded because, like if you just look on the picture here, I'm considering the set of all of these endpoints. Can anyone give me explain why? How do we know that set is bounded? The set of all those endpoints. Is it possible that those endpoints, bounded above? It's possible those endpoints somehow stretch as you go down the list here. They get bigger and bigger forever out to infinity. It's not possible. Can you say why? Yeah, these intervals, the intervals as you go down, they have to get narrower. In particular, this number here, whatever the rightmost endpoint is, that is an upper bound for all these red ones, right? Every red point must be less than that blue point that I circled. And so that means these are, if I consider just the red ones, they are a bounded set, which means the soup exists by the axiom of completeness. So this, let me just say, x is a real number by AOC, right? This is how we know that the soup actually exists and is a real thing that we can talk about. And in our remaining 7 minutes, we'll show that x is in the intersection. In our example here, if I took the soup of these numbers, actually the soup of those numbers would be 0. Those numbers are the set of all 1 over n's, where n is 1, 2, 3, etc. The soup of those would be 0. We're going to show that x is actually in the intersection. And what it takes to show that is, let me say it this way, it's enough to show that x is greater than or equal to an for all n, and x is less than or equal to bn for all n. In order to be in every single interval, what it means is the x is between the two endpoints for all of them, right? That's what it means to be in every one of those intervals. So we got 2 parts, x greater than or equal to an and x less than or equal to bn. I want to try to demonstrate both of those. Both of them will follow from the fact that x equals the soup of an, all right? Maybe in our remaining 5 minutes, I was hoping to have more time at this point in class. I want you guys to see if you can demonstrate one or the other or both of these. Maybe think about it. I will walk around and see if I can give you any more hints, if you want any more hints. Talk to your friends about it. Well, we'll see if we can get through this in 6 minutes. I don't know if we can. Or if not, we'll just start up at the beginning next time talking about these 2 things, all right? See if you can demonstrate that x is bigger than all of the an's. You will use the thing that I underlined in blue, the fact that x is it obvious? I don't know. Think about it. I will give you a moment to think, and then I'll walk around and see if I can help you out. I hope you don't mind me walking around. I'm not here to judge you. Not today, at least. Thoughts? You weren't expecting me to expect you to actually. You have to remember what the soup means. Any ideas?
Trying to picture it out like you.
Okay. Thoughts?
Yep.
X.
Yep.
So if it's soup, then it's the greatest of the AN soup.
Oh, this is upper bound.
Yeah.
So it is larger than that.
Yeah. So then it has to be. Yeah. I don't know about.
We got 3 minutes. Maybe we can talk about this in 3 minutes. So I know probably not everybody has finished. Maybe nobody has finished. It's fine. X is bigger than AN. That's because X is the soup, which means it's the least upper bound of the ANs, right? In particular, X is an upper bound of the ANs, which means it's bigger than all the ANs. So X, let me try and write that. X is the soup of the ANs. So X is an upper bound of the ANs. So X is greater than or equal to AN for all N, right? Because it is an upper bound, okay? We have not yet used the fact that it's the least of all the upper bounds. That's, well, maybe we'll use that in the second part. We got 2 minutes left. Anybody think about the second part? The second part will involve the fact that it's the least. Yeah.
Yeah, I'm saying because they're all nested, then for all Bn in the set, then Bn minus 1, or plus 1 has to be less than Bn.
That's true.
That's all, that's part of it.
Yes, that's true. Although I'm not sure. I'm
I'll
not
let that help.
sure. Yeah, how to. What do you think?
Wouldn't it like kind of just be the same as the AN because X is the soup of AN, X is less than or equal to BN, so AN is greater than or equal to BN.
So we have to explain why X is less than or equal to Bn, right? I think you just said that as part of. Yeah. Oh no, the clock just went over. Here's what I would say. Because of the nesting, and maybe this is related to what she said a moment ago. Every Bn is an upper bound for the set of ANs, isn't it? Like when you look at the way that they're nested, the B's are these blue ones, right? And wouldn't you agree that every one of the B's is an upper bound for the red things, right? It's because of the way that they're nested. Well, if X is the least of all the upper bounds, then it means that X must be less than all the B's, because all the B's are upper bounds, all right? So every Bn is an upper bound for AN, since X is the least upper bound. Then we have X less than or equal to all the Bn's. All right? Shoon. All right, I think that'll do. Sorry I went over by 1 minute. It's a little tricky. Nothing we can't handle.